Hello and welcome back to the IB Chemistry November 2025 TZ3 Paper 1A walkthrough. We're just going to be continuing with Paper 1A for HL, starting at number 11, going through questions 15. If you're looking for the rest of these videos or a specific question, go ahead and look at the playlist and find it. And so number 11, this is a classic question where you're counting the number of sigma and the number of pi bonds. However, this is a skeletal structure. Okay, and so the trick is they want you to just go, okay, sigma, sigma pi, pi, and just do that. However, there are carbon-hydrogen bonds that are missing here, and those are all sigma bonds. Okay, and so rather than just redrawing this as like H, that gets really messy really quickly. And so what I do is I just draw a star by each carbon to represent how many hydrogens there are. So at this one, we have a carbon that is singly bonded to something. So we need, it's a CH3 group. So we're going to put 1, 2, 3. Cool. Meanwhile, here we have a carbon that is double bonded to something and then singly bonded to something. So it has 3 bonds already. So it needs 1 hydrogen. Same thing with this carbon as well, 1 hydrogen. Meanwhile, this one has 3 and then 1 bond, so it already has 4 bonds, and our nitrogen does not need any hydrogens, or else it would be shown. Okay, it just has a lone pair of electrons. And so in terms of counting our number of sigma and pi bonds, if we have a single bond, it's going to be just 1 sigma. If we have a double bond, it's going to be 1 sigma bond and 1 pi bond. And if we have a triple bond, it's going to be 1 sigma and 1 pi. And so by default, just with our hydrogens, our carbon-hydrogen bonds, we have 1, 2, 3, 4, 5 sigma bonds. So we have 5 sigma bonds just from the carbon-hydrogen bonds. And then now we can count for just our regular bonds. And so like here, we have just a sigma bond. Meanwhile, with this double bond, we have 1 sigma, 1 pi. This single bond, just a sigma. And then that triple bond, 2 pi, 1 sigma. And so in terms of our number of pi bonds, is we have 2 from that triple bond and 1 from that double bond. So that's going to be 3 total, which brings us between C and D. Meanwhile, our sigma bonds from our non-carbon hydrogen bonds, it's going to be 1, 2, 3, 4. And so 4 plus 5 is going to be 9, therefore leading us for D to be our answer for that number 11. So this question number 12 seems very simple. Which element is a p-block metal? And so the very important thing is that I think a lot of students would just see p-block and then answer based on that. However, the important thing here is metal. This is not metalloid. And as much as you forget they exist, you should have the staircase of metalloids memorized because they are not on your data booklet. So we're going to go over to our data booklet and look at our periodic table over here. I'm just going to here as well. And so immediately we're going to look at our options. So our first option is SN. So we're going to, there is our SN. Cool. Meanwhile, we also have TE, so tellurium. There we go, tellurium. And also I'm going to go ahead and highlight which ones that I just remember off the top of my head as being metalloids. So we have our boron, our silicon, germanium, arsenic, tellurium. And I believe that's our staircase, if I'm not mistaken, antimony and tellurium. And so if we look at our options, we also have CD, which I'll even highlight in a different color, or other options. So we have SN, we have TE, we have CD, and then we have AT. Boom. Cool. And so immediately based off of that is I'm immediately starting to think, okay, in terms of which one is a p-block metal, is one as our p-block is boop, boop, boop. Let me get a different highlighter. Let me go yellow. This is our p-block. And so automatically CD is disqualified because of the fact that it is a transition metal. Okay. And so on the other hand, tellurium, I know that for sure is a metalloid because I made a fake exam question about it based on the fact that it was a metalloid. It's one of the great examples. So I'm going to go ahead and cross that out. And so we're left with AT and SN. And so if you look at, in terms of the metalloid staircase on this side of your metalloid staircase, you've got your nonmetals. On this side, you've got your metals. And so it does lead us to SN10 being the correct answer. And so the correct answer, this one is going to be A, because AT is going to be a nonmetal, CD transition metal, tellurium, and alloy, and SN would be our P block metal. Moving on to this number 13, we have this question that is asking about which two elements form a compound with the strongest ionic attraction. And so this is essentially just a code word for asking for the highest lattice enthalpy. Okay, because lattice enthalpy is essentially how much energy it takes to break a lattice, which is essentially a measure of an ionic attraction, right, within a lattice. And so lattice enthalpy is going to be based on two things. It's one, the charge, and two, the atomic radius. Okay, so for instance, if you have two things that are made of ions that are +2 and -2, or compared to something that's +1 and -1, the one with the higher charge is going to have a stronger attraction and going to require more energy to break the lattice. So we're going to look at the periodic table and see what charges are in these ions. And so obviously you're literally just going to be going, okay, wow, +1, +2, +3, -1, -2, -3. That's how you can tell the charges of the ion. So Li is going to be plus, O2 minus, plus, 2 minus, plus, 2 minus, plus, 2 minus. So there's no difference in the charge for any of these. And so that's when we go on to ionic radius. And so in terms of remembering whether bigger radius, smaller radius causes more kind of attraction, this is when you can think of, because attraction, literally think of people. If you have a couple that is really close, they're in love, they love each other very much, that one couple at school that has a lot of PDA, and you're like, can you all stop it, right? They're annoying. And so if they love each other very much, they have very strong attraction and they're very close to each other. So smaller radius, higher attraction, and requires more energy to break the bond. Okay. Meanwhile, if you have a larger radius, you hate each other, and therefore you require less energy to break your bond because you don't really have a very strong bond in the first place. You hate each other. And so we're going to look to with the pair of elements that have the smallest radius. Okay. And so we can actually draw out these elements on the periodic table, where if you like, you can look over here in your data booklet as well. And so you have Li, Na, K, and then you have O, S, S, E. So Li, Na, K, O, S, and S, E. Okay. And so the atomic radius trend is boop and boop. Boop and boop. Okay. And so I always remember this because all of the other trends are the opposite way around. Radius is the odd one out. Okay, that's always how I remember it. Is we're going to look for the smallest radius. So what's it called? Small, big, small, big. And so if we're looking out of our Li, Na, and K, our smallest radius is going to be our Li. And if we are looking out of O, S, and Se, O would be our smallest radius, and so Li and O, so A, are going to be forming the strongest ionic attraction and have require the most energy to break their bond in an ionic lattice. Number 14 is another one of the periodic trends, a classic about the oxides. And so this is literally, you need to know literally just this, which is that as you go across a period, boop. And so as you go across, in terms of the oxides that are formed, your non-metal oxides, so your ones that are the furthest on the right, are going to be forming your most acidic oxides. And your ones that are the farthest left, your metal oxides, are going to be forming your most basic oxides. That is it. And so you're going to look and just see which ones are which. So our magnesium, that is our metal, and it is the most left on the periodic table. Therefore, the answer is A. Aluminum is going to be amphoteric. Therefore, it could form either basic or acidic oxides, depending on what it is reacting with. Silicon and sulfur, they are both on that right side. Even though silicon is a metalloid, it's still further right. And so it's going to be forming an acidic oxide, just weakly acidic. And then sulfur is going to be forming a very acidic oxide that contributes to acid rain. So magnesium oxide, that one is going to be the most basic. So number 14 is A. Okay, so number 15, this last kind of question for this video is going to be, which statements best explain why copper 2 ions are blue in aqueous solution? And so we're going to look at each one and see whether it's true or not. So for this first one is copper 2 plus ions are going to be absorbing orange light. And so before we even honestly move on to the rest of the questions, we're just going to explain how color works, okay, in case you forgot. So you have a little test tube of, say, some copper 2 plus ions. So I'm just going to go copper 2 plus, okay? And so some light, so like just say white light, which contains all the colors, is passed through the solution. And so obviously light contains energy. And so copper 2 plus is a transition metal, which essentially means that its d orbitals, which are normally like 1, 2, 3, 4, 5, like our 3d, are split into these higher energy and these lower energy. I'm not going to label them explicitly because you don't need to know it that deeply, but you have higher energy and lower energy. And so there is this gap in between those energy levels. Sorry to interject past me, but me from the future, I did split them as being 3 orbitals, 2 orbitals. It's actually the opposite. So rather than 3 and 2, it is 2 and 3. You all don't need to know this. This is just purely for technicality reasons. I just don't want to get called out in the comments by someone going, well, technically. So correcting myself here. Okay. Past me, continue the explanation. In which an electron can be promoted if it absorbs the right amount of energy. And so this light, which contains energy, hits this test tube with our copper 2 plus solution. And so orange light is essentially just the wavelength that happens to correlate with this energy gap. And so whenever orange light is absorbed, these electrons in this lower energy level have enough energy to be promoted. Okay, and eventually, obviously, they fall back down. But what we're concerned about is the promotion. So they are promoted, they absorb this orange light. And so in terms of the way that our eyes perceive color is light, like that's passing through initially, contains all the colors. Whenever orange is passed through and it is absorbed, we see the complementary color. And so orange light, I'm just going to put absorbed. And so on the other side, our eyes, is we see the complementary color. I'm just going to put like eyes. Woo! So we see, which is going to be blue. And so to see if number 1 is true, we just need to make sure that orange and blue are complementary colors. Okay, because if we see blue being emitted, then that means that the complementary color must be being absorbed. And so if we look at this section 15, blue and orange are on the opposite sides of the color wheel. Therefore, that is correct. And so number 1 is true. Meanwhile, number 2, this looks like it may be true. You're saying, okay, blue light is emitted as electrons move to lower orbitals. Okay, and so it's essentially describing the fact of going, oh, like these electrons are initially promoted, and they do at some point have to fall back down. What comes up must come back down at some point, right? However, the reason why we see the blue is not because of that emission of these electrons coming back down. Is we see the blue because of the absorption of the orange. Okay, it's just the way that we perceive it. Okay, and so number 2 would not be correct. Is yes, blue light is emitted, but that's not the reason why. Blue light is emitted because those copper 2 ions absorb orange light. Okay, meanwhile, 3 electrons are promoted between d orbitals. Like I said previously, is your 3D is split into a higher and lower energy level. And so that electron is going up and then coming back down. And so, yes, that one is true. It's just a matter of the absorption is what is really responsible for the light that we see and the color that we see, not the emission. Even though it is happening, that absorption is what is causing it. And so in this case, 1 and 3 are going to be the only ones that are correct. And so this one would be B. And so another little thing in terms of the terminology I kind of do want to emphasize here is that whenever we say like, blue light is emitted, it actually would be more accurate. We're basically saying it's because of the absorption, is that rather than saying emitted, to make it more accurate, is we can say transmitted. So it's not really like it's actually being emitted. It's more like we're just saying everything that was not absorbed. Okay, 2 different things.